Okay, so welcome to today's lecture. So we have two lectures, one now and another at 2 p.m. in the afternoon. So the speaker is Ameya Jagtap. He got his PhD from aerospace engineering in IISc. Currently, he is a professor in Brown University. His research interests are in traditional methods like spectral, finite element, we know DC schemes for hyperbolic problems and PDEs in general. And apart from that, he also works on scientific machine learning, deep learning, physics-informed machine learning, and such topics and their applications. So this is, as you know, very rapidly and explosively growing area, and it's sometimes hard to keep up with the developments. But he is someone who is very much in the middle of the research that's going on, particularly in physics, PINNs, physics-informed neural networks. So it's a great opportunity to listen to him and maybe learn from him. And also, as it's a very practical, hands-on subject, right? So if you work in this area, you can directly interact with him and get some tips or etc. Right? So please, you can start.
Thank you, Praveen sir, for the nice introduction. Yeah, first, so we will start with lecture 1. So basically, here I'll just introduce the basic deep learning concepts, and then we'll move to the physics-informed deep learning things. So I'll start with the acknowledgement first. So I would like to thank both Professor Vasudevamurthy and Praveen sir for this, because it was Murthy sir's idea back in 2020 and 2021 we started working on this, but unfortunately we couldn't materialize it. But thanks to Praveen sir who gave me this opportunity to give this short course. Okay, I must admit that it's difficult or it's impossible to cover everything. Sorry. Yeah. It's difficult or impossible to cover everything in one day short course. So basically, I'm going to keep it very simple, and I won't go too much into the details. But you are always free to reach out to me if you have any questions. So in the first lecture, as I said, I will discuss the basic concepts of deep learning, and then we'll move to the physics-informed deep learning thing. And in the second lecture, we'll see some of the limitations of physics-informed deep learning, and we'll also see some performance improvement techniques for the same, how we can overcome those limitations. That we'll see in lecture 2. Okay, so let's start with the overview of lecture 1. So same thing. So we'll discuss basics of deep learning, and then we'll move to physics-informed deep learning. So we'll be having some examples, coding examples. For that you need a TensorFlow 1 or 2, Python 3.6 or above, and LaTeX for plotting figures, basically. So if you're comfortable with any other ML libraries, that is also fine, like PyTorch and JAX. Nowadays, it's very easy to write a code. You just ask a ChatGPT to write a code for you, and you will get everything. So you don't have to write a code from scratch. Those who are online, for them, this is the GitHub repository, physics-informed deep learning, from where you can download the code. And we will also see, we'll also discuss some other codes which is available on this GitHub page. Okay, so AI, or artificial intelligence. So AI has revolutionized both academia and industry. It has actually achieved remarkable success in many applications. So for example, healthcare, online shopping, autonomous vehicle, stock exchange, space exploration, or even creating an artificial music here. So what is AI? So basically, it's Wikipedia definition. So AI is the intelligence of machines as opposed to the intelligence of humans or animals. So in this course, we are particularly interested in deep learning, which is a subset of machine learning, which itself is a subset of AI. You can see that this is a deep learning, which is a subset of machine learning, which itself is a subset of AI. So deep learning is a type of AI that involves training computer models to learn and understand patterns and information from the data. So this is what similar to our brain works. So it uses neural network to understand these hidden patterns and using the set of artificial neurons, the interconnected set of network of artificial neurons that actually process the given available data. Okay, so here is the example. This is a feed-forward neural network. This is the most common neural network that has been used in deep learning community. So the term deep in deep learning refers to this multiple layers of the neural network, and each layer learns and extract increasingly complex features and representation from the input data. So we will discuss this shortly. What are these features and representation? Okay, so by combining these layers, the model can learn to recognize and understand the relationship within the data set. So if you have input-output data set, you're trying to learn the relationship between these two data sets. Okay, so let's see what are the types of deep learning algorithm. So the first one is supervised learning. So basically, in this case, the model is trained on the label data, with each example having a known input and output. So in this case, you know the input and output pair, and you are training the model to learn this mapping from input to output. And the goal is to develop a mapping from input to output such that model can make prediction on the unseen data set. Second one is the unsupervised learning. So in this case, your data is unlabeled. You don't know what the data is, but the purpose is to discover the hidden pattern or structure in the data. And the third one is the reinforcement learning. Here, model learns to make decision based on the feedback from the environment. Okay, so some of the examples of this supervised, unsupervised, and reinforcement learning are given here. So basically, in this lecture or in this short course, we are actually focusing on the supervised learning. So in this case, we have both labeled data sets, the input-output pair. Okay.
Okay. Question?
Hello. Yes.
Can I ask a question? I'm Shrikar.
Yes. Yes.
What do you mean by label?
Label means you are actually defining what is your output is. So if you have a mapping in PD sense, if you have input x and y as the coordinates and the output u, so you are actually defining what is u here.
I understand.
Yeah. Well, in case of classification, you are defining if you are classifying an image, whether it's a cat image or dog image, then you have to label that image, whether it's a cat or dog. So that is called label data.
Okay, thanks.
Okay, so the first question is why we need deep learning, or in particular neural network. Okay, so this is because of this theorem, universal approximation theorem. So there are many versions of this theorem. First came in 1989 by Saibenko and Hornick, and recently by Professor Musker, Professor Hrishikesh Musker. He recently visited Brown. So basically, this theorem implies that neural network can represent any kind of continuous function with appropriate setting of the network parameters. So this is basically an existing theorem. So it does not provide any construction, how to construct that neural network, but merely states that such construction is possible. Okay. And to construct these parameters, typically neural network uses optimizers, which may or may not converge to the correct weight. Okay. And one more important thing here is this theorem does not tell about the generalization aspects of the model, how well it generalizes. So we'll come to that, what is generalization and all. So, but yes, it's because of this theorem, people started using neural network. Okay, so let's see the most basic form of the neural network, which is called as perceptron, proposed by Rosenblatt back in 1960s. So you can see these are the input x1 to x6 here. These are the input set. W1, W2 to till W6 are the weights. B is the bias. It's a vector. And you are actually doing some kind of operation on them, and you are actually passing it to the activation function phi. And then you will get the output. Okay. So every input represents a feature of the input data and is assigned a weight W that defines how much the feature contributes to the final output. Okay. So bias B represent a constant offset that aid in shifting the decision boundary of the perceptron. So if you see here, this is the output, which is equal to phi. Phi is the activation function times summation Wx Wi xi plus bi. So why we need bias? So basically, there is one more reason to use bias, because sometimes this matrix vector product can give you zero vector, right? Even though both W and X are not zero. So in order to prevent that, we are actually adding the non-zero bias vector. Okay, so you cannot actually passing a trivial zero solution as an output. Okay, so that's why we need a bias vector. Okay, let's move on to the more general form of perceptron. It is called as multi-layer perceptron, or other feed-forward neural network, or FFNN. So which is consists of several layers of the network. So you can see this is the output, this is the input layer X, output layer is U theta, and these three middle layers, they are the hidden layers. Okay. So the term feed forward refers to the fact that the information flow through the networks only in one direction. So the information is flowing from X to U initially. That's a forward propagation. So we'll discuss these things in shortly. Okay, let's see the general setting of feed forward neural network. So for example, if you have a neural network of D plus 1 layers, which consists of one input layer, D minus 1 hidden layers, and one output layer. Okay. So in the ith hidden layer, we have Ni neurons that actually receives an input Xi minus 1 from the previous layer. And then you actually do the affine transformation of this form. So you are just multiplying the weights with the input and then adding the bias. So, and now you are actually sending this to the activation function before it goes to the next layer. Okay. So yeah. So again, Wi and Bi are Wi is the matrix, where Bi is the vector associated with the ith layer, and these are actually initialized from independent and identical samplings. So we'll see the initialization methods for these parameters shortly. Okay, so the phi is the activation function. As I said, it actually, you have to send it to the activation function before it goes to the next layer. And the output is given by this expression here. So you can see the input layer X, it goes to L1 and then phi1, phi, and then till LD. So this circle is the composite function basically. Okay. And you can also represent your parameters Wi and Bi for all layer I, which is equal to the theta. So theta consists of my set of parameters. Okay. Yeah. So weights basically a matrix, so which is basically connections, but the bias is not a matrix, so it has just one value for each neuron. So that's why it's a vector quantity. Okay, so that's why their dimensions are different. Yeah. Activation function, basically it's a nonlinear function, so that incorporates nonlinearity in the model. So most of the problems are nonlinear, and if you want to capture those nonlinear features, then you need, because if you see, this is basically a affine transformation, right? There is no nonlinearity here, but then there is no way you can actually capture the nonlinear features using just an affine transformation. So that's why you need an nonlinear activation functions. Yeah, we'll come to that. Yeah. So there are so many activation functions that has been proposed in the literature, but there are some we will discuss here. Yeah. Yes. Before going to the next layer, there is an activation function. Yeah. So output, there is no activation. So output is a linear function. That's a good, but you can always put an activation function after this LD layer also. If you know something about the output, say for example, if you are predicting a fluid flow density, and you know that the density is always positive, you don't get negative densities. So you can actually use an activation function which actually like ReLU, which actually gives always an positive or zero value. Yeah, but sometimes if you do not know, then you don't put any activation function. Don't. Sorry? Yeah, but I think it should be D+1. Yeah, that's true. Okay, so let's see the learning procedure of the feed-forward neural network. So you can see this. So there are 3 steps. So basically, it's a forward propagation. The information is propagating from the input data to the output data. Okay, so basically the input data is fed into the neural network, which is processed subsequently in each hidden layers of the network till you get the predicted output at the end. Okay, so the next step is the loss function. We'll see how it is, how you are calculating this loss function. And third one is the backward propagation, where you are updating the parameters based on the loss value. So loss function, so we are actually, the predicted output is compared with the actual output. So since we are actually doing the supervised learning, you know what's the actual value, and what you also know what is the predicted value out of the neural network. And there are so many losses like L1, L2, or Huber loss, which combines both. In this case, I'm showing the L1 loss here. So you have the neural network output U theta minus U exact. So that's your loss function. And your aim is to minimize this loss function so that the distance between these two actually reduces. Okay. And the third and the important step here is the backward propagation, also called backpropagation or backprop. Okay. So here the aim is to minimize the loss function by adjusting the parameter theta. Here I'm showing the gradient descent algorithm, which is the most basic update formula for these parameters theta. So you are just updating theta at n+1 level using theta at n, the previous iteration, minus NL. NL is the learning rate, which is a user-defined parameters, multiplied by gradient of the loss function. So basically, it's the steepest descent direction. Okay. Now the aim is to find out this gradient of loss with respect to theta. So in our case, we have weights and biases, right? So our aim is to actually calculate this gradients of loss function with respect to weights and biases. Okay, so that's how you are actually using the you are updating the parameters. Okay, let's take a simple example. So this is a you have one input, you have just single neuron, one hidden layer. Okay, so this is total, it's one hidden layer, and then you have output u theta. Okay, so you have just weight W1 here, you have just one bias. After L1 is basically the, I'll put it here. So L1 is basically the affine transformation, which I have shown earlier. And then after that, you are applying an activation function. Okay. And then you are supplying, you are multiplying again with W2 before actually giving the output U theta. Okay. And once you have the output, you can calculate the loss function. I have already shown, either use L1, L2, or Huber or any other. There are so many types of loss function. Okay, so here I just use the L1 loss function. So since we have just one point, there is no summation here. Okay, so and I'm actually replacing the neural network output U theta with the exact value W2A1 minus U exact, which will be given. Okay. So in the back propagation, we need to evaluate these gradients with respect to theta. So now theta consists of W1, W2, and bias. Okay. And I just use chain rule of differentiation to find out these quantities. So for example, for gradient of loss with W1, you just use the chain rule here. Okay, I'll show you pictorially here. So you can see that you have loss and you are taking the gradient with respect to A1 first, and then L1, and then W. So that's how the chain rule of differentiation works here. Okay, and similarly, yeah. Because it actually depends on more than one variable. So you have W1, W2, and B. It's not total. It's not just one variable. Yeah, I'm loosely representing the absolute value. Yeah. Okay, so similarly, you can actually find out the loss function, gradient of loss function with respect to W2 and B. So any questions here? Okay. Okay, so let's move into more details of this loss, how to calculate the gradient of the loss. Basically, we use automatic differentiation. So this automatic differentiation is one of the factors that has contributed to the success of deep learning, and it enables quickly compute gradients evaluation for the composite function. And basically, it actually gives the machine precision accuracy for even for higher order derivatives. But yes, there are some pitfalls of this automatic differentiation, which we will see later. For example, if you are solving a hyperbolic conservation law where the information is propagating from a particular direction, it does not actually account for that. So it takes derivative like from all directions. So it's like central difference formula. Okay, and that can be a problem for solving the hyperbolic conservation laws. Okay, so let's define following variables. So we have Wj minus n. So these are the number of input variables. Wj is the number of intermediate variables, and Yk minus j, which is Wl minus j, is the number of output variables. So let's take an example again. So if we have the function f, which is from R2 to R1, and yeah, so this is the function here, and we are trying to evaluate the derivative at these points x1 and x2. Okay, and we'll okay, so we'll actually record the intermediate value. So let's define these input variable intermediate variables and the output variables. So if you see here, the input is R2. So we have X1 and X2 is the input. So we start with W-1 and W0. So these are the input values. And the numerical values at X1, X2 is 1, 2. So basically, these are just 1, 2 value. And then we are finding W1, W2, W3, and W4. So these are the intermediate variables. So you can see that W1 is W-1 by W0. So this value, this ratio. W2 is cos of W1. So we have this value. W3 is exponential of W-1. This. And W4 is W1 plus W2. So basically, yeah, so these two. And finally, we are subtracting W4 from W3. So basically the exponential term we are subtracting. And that's my output, W5, which is equal to Y. Yeah. Yes. Yes. Yeah. Yes. Yeah. So why the output is Y. So it's just scalar value. Okay, so here aim is to calculate dy by dx, 1. Okay, so and we will use two modes of automatic differentiation. So namely forward mode and the reverse mode. Okay. Okay, this is the computational graph of the previous table. So you can see the forward mode. So in the forward mode, we are actually starting from the input data, X1 and X2. And we are trying to calculate the output, Y, derivative of Y. And in the reverse mode, you start with output and you are actually going in the backward direction, reverse direction towards the input. Okay, and this computational graph you can actually easily write down based on this table. So you know which weight is connected to which weight, and then you can actually draw these directions basically. So this is the computational graph. So let's start with the forward mode AD. Okay, in forward mode, the independent variable with respect to which the differentiation is conducted is fixed initially, and the derivative of each sub-expression is computed recursively. So basically, in this case, the independent variable is x1, and we calculate wj dot, which is equal to derivative of wj with respect to x1 for each wj. Okay, so as I said, forward mode starts from the input and it goes towards the output. So you have W-1, which is X1, W0, which is X2. You find out derivative with respect to X1, which is 1 here. And with respect to X1, derivative of W0 is 0 because there is no X1 here. And then these intermediate variables. So similarly, W1, W2, W3, and W4, which we defined earlier, you can find out these derivatives and you can actually write the numerical values at X1, X2 equal to 1, 2. So these are the numerical values. And finally, you get the derivative of output Y1. That's what our aim is, to find out this dw dy by dx1. So this is the answer. So before saying anything on this, commenting on this, let's see the forward mode. And then we will see the comparison between forward and the reverse mode AD. Okay. So yeah, so the values of W are sometimes referred as primal traces, and their derivatives are as referred as the tangent trace. So let's see the reverse mode here. So reverse mode, also called as adjoint mode, okay, that calculates the derivative by going from the end of the evaluation trace to the beginning. So from output to input. So the adjoint is defined as W bar, and basically it is defined as a derivative of Y with respect to all Wj. So W bar j is equal to +1. Okay. Okay. So in this case, we are starting with output Y, and we are finding these adjoints, which is actually trivial. So you just need to use chain rule of differentiation if it depends on more than one variable. So this is the output W5, which is W4 minus W3. And this is the adjoint value here. And then similarly, you can calculate adjoint values for all from W4 till W minus 1. Okay. Okay. If you see last two rows, so you can see that you actually get the derivatives of y with respect to not just x1, but also with respect to x2. Okay. So you can see the advantage here, basically. So the forward pass need two forward pass to calculate these derivatives. So you need to go 2 times. Okay. But reverse mode gives you this derivative in one shot. Okay. So if you see, you have both a derivative with respect to x1 and derivative with respect to x2. Okay. So that's the advantage of reverse mode. So in general, if you have function f which maps from Rn to Rm, and if n is greater than m, then the reverse mode is preferred, which is of the order of m. Whereas in case of when n is less than m, then forward mode is preferred. Okay. So if you see the loss function is a scalar value. Okay. And if you want to find out the derivative of loss function with respect to the parameters theta, so that's why you actually use the reverse mode, because most of the time the input dimension is always bigger than the or the parameter dimension is always bigger than the loss function dimension, which is scalar. I think I need to connect. Okay, so you can choose forward mode or reverse mode depending on the dimension here. Yeah. Yes. It's no, because in reverse mode, I said that when n is less than greater than m, then you need to use reverse mode because it has low comp. Yes, yes. Otherwise, go for a forward mode. Okay. Now you know something about automatic differentiation that has been extensively used for training the neural network model. Yeah.
In the layer form, like if we take perceptron, where what are the values which are recorded? Like we are going back, like in forward pass also and backward. What values we are recording and then comparing to find out that value?
So you said so this one.
Yeah,
or okay.
We are going to backward pass.
Yeah.
So we are same value.
Yes.
So what values are recording like in comparison to that we are applying same value?
So basically, what you are doing is you are finding the gradients of the loss function with respect to the parameters, right? And automatic differentiation use some either forward mode or reverse mode. So what you are calculating is all these, that's what I explained that, right? Okay. This one. Yeah. So what you are calculating is the adjoint values. But you don't have to calculate all this by yourself, because AD packages are there. So you just need to call the AD package to find out this.
So like depending on how many input variables are there in one backward pass.
So this is, we are not differentiating. We are basically differentiating with respect to the parameters. Yes.
So how many parameters we are having at the last of that backward pass? It will calculate with every parameter. X1, X2,
so yes, if you have input say x1 to xn, so the reverse mode in one shot, it will give you the whole set of parameters. So basically, the thumb rule is the forward mode gives you the directional derivative. So it will give you derivative only in one direction. So for example, in this case, you get just dy by dx1. Okay, but the reverse mode will give you full derivative. So whatever the number of variables you have, input variable x1 to xn, it will give all the derivatives. For forward mode, yes. In one shot. Yes. So it will give you full derivative, whereas forward mode will give you the directional derivative. Okay, let's see the parameters versus hyperparameters. So you already know the parameters of the networks like weights and biases. Okay, so there are other parameters that can be included in the network, such as adaptive learning rates and parameters in the activation function. So you can parameterize the activation function, and you can also learn the parameters of that activation function along with the weights and biases. Okay, but there is something called as hyperparameters. So these are not the parameters which you are training, which you are evolving. So these hyperparameters are the actually these are user defined parameters that you need to define it before you start the training. Okay. So there are various hyperparameters. Say, for example, learning rate, which we have already seen in the update formula. You have NL, which is you need to define the learning rate. Well, there are some ideas where people have used the adaptive learning rate by parameterizing it. Then number of layers, number of neurons in each layer, right? So these are all hyperparameters. Okay. But then there is a concept, different concepts of like dropout. So you start with a very big network, okay, randomly choosing the number of neurons and number of layers, and then you drop the neurons if it does not contribute to the output layer. And that actually you can find out based on the weights. So how much the weight is. If weight is almost zero, just drop it off. So that's how you can actually start with a bigger network and then goes to the very efficient, smaller network. But that it all depends on the problem at hand. I mean, you cannot use the same network which you are training on one model, one problem to the another problem. Okay, so let's see the activation functions here. So again, it's a hyperparameter and you need to define it. And as I said earlier, this basically introduces the nonlinearity in the solution. Okay, so this is important when you want to actually capture the complex features in the output. Okay, and there are so many activation functions used. So earlier one that was defined by Rosenblatt, they use a step or Heaviside activation function. Okay, and then people started using sigmoid activation function. It's defined here, and it has range from 0 to 1 and infinitely differentiable. Okay, and then hyperbolic tangent activation function, they started in late 90s. We have compared the more than 180 activation function in this survey paper, so you can take a look. Okay, ReLU is another popular activation function that has been regularly employed in classification task. And this is a ELU function, exponential linear unit, which is also used in many applications like computer vision and natural language processing. Okay, so well, there are, as I said, many activation functions. So there is no thumb rule how to choose these activation functions. So what people use, they actually define an adaptive activation functions. So you parameterize the activation function, and then you learn these parameters along with the weights and biases. So this way you don't have to worry about which activation function should I start, right? Because a priori you cannot, there is no thumb rule to choose this activation function. Yes, for computer vision, people have done a lot of experiments, and like there is a family of ReLU activation function that has been regularly employed, and it gives much better accuracy than the other activation functions. Yes. I mean, that's what, as I said, these are people have done some comparison, but the best idea is to start with adaptive activation function, because then it can evolve as per the problem at hand. So you don't have to worry about how to choose the activation function.
We need not to define first, like what we are choosing, or like at particular.
No, we had to initialize. I mean, what we had to choose some initial activation function with some parameters.
So we are not doing that. How to change this activation function after some cost?
No. The point here is what the idea is. You are updating these parameters along with weights and biases such that your loss function decreases. So they will update in such a way that it will use smaller and smaller loss. So we will come to that in second lecture. We will see in the performance improvement technique. We'll see this adaptive activation. Okay. Okay. So let's discuss this optimizer. So basically, the optimization process is machine learning is to find the set of optimal parameters that actually reduces your loss function. Okay. So stochastic gradient descent is one of the basic or widely used optimizers. So here idea is in the gradient descent method, you use the whole set of data. But in stochastic gradient, you actually randomly choose the, data, few samples, okay, to find out the gradients. So this is much more efficient than the gradient descent. Now there are other variants like ADA-grad that actually adapts the learning rate of each parameter based on the historical gradient of that parameters. It is more effective than stochastic gradient descent. And then there is ADA delta. So these are all recently developed optimizers. So in case of ADA delta, instead of using the entire history of the gradients, they just use the recent gradient. Okay. Adam is one of the popularly used optimizers for pins, basically. So it has you start with Adam, and then you switch to Adam, basically a first order optimizer, and which you just need a gradient, you don't need a Hessian. You start with Adam for say few thousand iteration, and then switch to more second order optimizer like LBFGS. So LBFGS, again, since it's second order, it need information from the Hessian matrix. Okay. The idea here is when you start with Adam, you actually avoids the local minima, basically. So you don't want to stuck in the local minima because there are so many local minima, and each local minima may not give you the optimal solution. Okay. And once you go to LBFGS, it actually accelerates your conversions. So we'll see those results in the coming slides. And then there are so all these optimizers are gradient based, and then there are gradient free optimizers like genetic algorithm and particle swarm optimization. So recently there is one paper who uses PSO for pins, and they have claimed that the results are much better compared to Adam optimizer. Okay. So we'll see some of the effective training techniques for this model. So we'll first see how we can actually initialize the weights, then batch normalization. So before passing your input to the next layer, we need to normalize it. And then we can also use mini batch. That means a set of small set of training data instead of the whole set. And then we'll see the concept of overfitting, underfitting, and the bias-variance trade-off. So let's start with initialization techniques. So there are different initialization techniques, such as random. This is the most basic. So you can actually choose random values from a known distribution, okay, defined like Gaussian, uniform, and truncated normal, okay. But this is not an effective technique because you cannot, I mean, sometime it has been shown that it actually explores the gradient during training. So then people have come up with the different initialization, like the this one is the heavier initialization, or it is also called as Gloret initialization. For a given layer with an in and an out input-output pairs, the weights are initialized from the normal distribution with zero mean and the variance of 1 divided by n in. Okay. So we use Xavier initialization for pins. Okay. And then there is something called as so basically here you are trying to make both input-output variance almost equal, basically. So the next one is He in initialization. So this is particularly they defined it for when you use non-symmetric activation functions like ReLU. But apart from ReLU, I'm not sure whether this initialization has any advantage over more general Xavier initialization. So in this case, again, you have to actually initialize the weight from the normal distribution with zero mean, and the variance is equal to 2 divided by n. Okay. And then there is this orthogonal initialization where we are actually set the weight matrix as an orthogonal matrix. The idea here is since the orthogonal matrix, the absolute values of eigenvalue is unity. So when you do all this metric multiplication in each layer, so it will not explode or vanish the elements of the matrix because of this orthogonal matrix property. No. So they are choosing from the random distribution, but we are making sure that, so for example, in this case, normal distribution, we are making sure that it has a mean 0 and the variance 1 by n. So they are different values. They are not same value. The distribution is given. Yes. Okay, let's move on to the batch normalization technique. Here, what we are doing is we are normalizing the input to each layer by adjusting the and scaling the activation. So basically, given a mini batch of size S and an input vector or tensor X, the batch normalization operation computes the mean mu B and the standard deviation sigma B of X. So these are standard formulas for mean and standard deviation. And the normalized input X bar, X hat, is given by X minus. So you just subtract it from mean and divide it by standard deviation. And this is a small constant you need to add for numerical stability. I mean, in case if standard deviation is very small, then it should not explode. Okay, so here is the another idea, mini batch. So instead of using the the whole training data set, you just use a subset of the training data to update the model parameters. Okay, so it is more efficient, computationally efficient, and second, you can actually process each data set in parallel. So if you have, you can easily parallelize this on GPU or TPU hardwares. So that's the idea. Second thing, if you have a large data set which you cannot fix, I mean, which you cannot feed it to the single GPU, right? GPU has their own memory, and if GPU saturates with just half of the data set, then you cannot run on a single GPU. So then you need a multi-GPU. There, you just go with the mini batch. Okay, so this is the important concept in deep learning or machine learning algorithms. So this is the bias variance trade-offs. So you can see this graph here. So the y-axis is the prediction error, and the x-axis is the model complexity. So if the model complexity increases, the bias actually it decreases, but whereas the variance increases. So what is bias? So bias is the error introduced by approximating a problem with a simpler model. Okay, so you start with a simple model and you have a large bias. But if you increase the complexity of the model by increasing the depth, width, okay, then your bias actually decreases. And variance is the error introduced by the model sensitivity to the noisy or random fluctuations. Okay, so with the complexity of the model, your variance increases. With simple model, your variance is low. So our aim is to achieve this balance with trade-off, where you have minimum, not minimum, but your total error is minimum basically when you add these two. So your total error is minimum. Okay. We'll see. This is basically, well, in this case, it's a generalization error. But you can also, generalization error consists of your estimation error, where you are having a finite set of data. Yes, and the approximation error. Okay, so yes, it is a generalization error. But then you also have the optimization error. So that has not been accounted here. Okay, so again, overfitting and underfitting, you can see these are the most basic problems that encounter in ML models. So you can see this is a regression problem, and you can see when these are the black dots are the data set, which noisy data set basically, which is available, and underfitting is it actually does not learn the model, does not learn the data. Okay, and if you see the overfitting is, I mean, it is actually fitting each and every data without actually understanding that there is a noise in the data. Okay, and optimal fitting, that's what you need, where you are balancing both bias and variance. So in this case, underfitting you have high bias, overfitting you have high variance, and the optimal fitting is where your bias variance balances. So underfitting, again, when the model is too simplified, it fails to capture the underlying pattern in the data. Model is not complex enough. So that means you have large bias and low variance. And overfitting, when the model is very complicated and closely matches with the noise. So you can see it here. Okay. This is due to, again, large variance and the low bias. Okay, so there are different kind of neural network architecture that has been employed in the literature, like convolution neural networks. They use it for computer vision, recurrent neural network. So basically, these are sequential models where you have a notion of a sequence. There are various variants of RNN, like LSTM, long short-term memory model, GRUs, and reservoir computing. Okay, these are the RNN or the sequential model are mostly used for processing a kind of a sequential data, like you are doing a natural language processing, from converting one language to another language. So you need to feed a sentence in the data in the model. So there it is useful. These sequential models are useful there. ResNets are just the skip connection between the model. We'll discuss this later. So basically, what you are doing, you are sending your input not to just the first layer, but also second or third layer. So this is called a skip connection. Okay. So because as your input progresses from first layer till last layer, some of the features get dropped out, and you don't want to drop out some important features of the input data. So you always feed input data to the subsequent layers after the first layer. So this is called as ResNet or residual networks. Okay. Then something called as graph neural network. So in this case, you can actually deals with the unstructured data. So you don't have to be in the Euclidean space. So if you have the, say, for example, this is useful for predicting the, for example, on the Netflix movie, they will give you the options to watch movies. So these are options predicted by your previous history. Okay. So these are all unstructured data because they are basically the connections, or even on the this kind of a social media like Facebook or LinkedIn, they gave you the recommendation to connect some particular person, right? Because it has same background as yours and same research interest or whatever. So these are all done by the graph neural networks. The next one is the transformer. Basically, again, it's kind of a it's basically the advanced version of RNN. So RNN is a sequential model. As I said, you have to feed the data sequentially. But in transformer, you don't have to feed the data sequentially. So you need to feed the whole sentence or paragraph directly. So the GPT uses transformers. Okay. But well, each architecture, there is a vast amount of literature, and it's not possible to cover all these things. So I'll just point out this. And for physics and from deep learning, we'll just use feed-forward neural network. So, but basically there are papers where researchers, they have used different architectures for physics and from deep learning. But in this short course, we'll stick to the feed-forward neural network. Again, the spiking neural networks are they are very close to our biological neurons, where the input data is in the form of spike. So that's how our brain works. So we get the data in the form of spikes. The advantage here is they are much more efficient than feed-forward neural network, but then it is always difficult to convert your data into a set of spikes. Okay, but recently there is some work where PINN has been employed. Spiking neural network has been employed in PINN framework. Okay, so let's come to our second part, which is the physics-informed deep learning. Okay. So traditional approaches like finite element, finite difference methods have undergone remarkable progress, but they still operate under very stringent requirements. Okay, so they need underlying physical law, the exact knowledge of underlying physical laws. They also need boundary condition, initial condition, and also time-consuming workflows such as mesh generation and long-time simulation. Okay, so in this case, I'm actually particularly focusing on the inverse problem, where you have a ill-posed inverse problem, and say, for example, you want to find a missing or the unknown parameters in the given PD. Okay, so in that case, if you use traditional numerical method, you have to run the code again and again by defining those parameters, right? So I'm talking about this box where you have some data available in the form of initial or boundary condition or any experimental data and some physics, not exact model, but some model with unknown parameters. Okay. Moreover, the given data could be dinky, dirty, dynamic, and deceptive. Okay. So dinky means it's not enough data, it's gappy data. Dirty, noisy data. Dynamic, and deceptive, it may be misleading. So if this kind of data is there, then definitely the traditional numerical method suffers. So what's the solution? You can actually use physics-informed deep learning techniques. Okay, So what is physics? Yeah. There are so many examples where you are finding the unknown parameters in the equation. So it's an ill-posed problem. So if you don't have enough data, and if you're trying to find, say for example, in solid mechanics, you are trying to find the compliance matrix coefficients, okay? Or in fluid dynamics, if you want to find the viscosity, which usually comes from the experiment. So you cannot, unless you know what kind of medium is, you cannot define the viscosity, right? But if you have data, for example, if you have velocity data and pressure data, then you can fit that into the Navier-Stokes equation with unknown viscosity and train the PINN model or physics from deep learning model to learn the viscosity coefficient. So what is physics-informed deep learning? So basically, this is the dictionary definition. So it is the process by which the prior knowledge stemming from the observational, empirical, physical, and mathematical understanding of the underlying model can be leveraged to improve the performance of ML or deep learning algorithms. So by incorporating physical laws in these machine learning or deep learning algorithms, we seek to build scientifically accurate predictive models. So basically what we are doing when we are actually incorporating physics in the form of governing equation in the neural network model, so it constrains the space of admissible functions. So the solution space is again constrained. It reduces, okay, because of the additional constraint given by the PD model. The solution should satisfy PD model and the data in order to, you can take that as one of the possible solutions. Okay, so this actually accelerates the training of the model with data efficiency. So data efficiency means you can actually use small amount of data when you have physics. Okay, and it actually increases the interpretability of the ML model that makes them more robust and trustworthy. So there are three approaches how to make this deep learning model physics informed. So first one is the observational bias. That's amount to the training of the model that reflect the underlying physical principle at the first place. That means you need to supply lot of data in order to incorporate the physics, which may not be possible always. So second thing is the inductive bias. So here that amounts to designing specialized priors and architecture such that physical principles are encoded inclusively in the model. So that's what I said, that you can actually define the activation function in such a way that you get always positive value if you are actually inferring the density. Okay, so this is the way to make changes in the architecture. Okay, and the third one is learning bias. So basically what you are doing, it's a penalty constraint. You have the additional constraint which you put it in the loss function. Okay, so what we are going to do is the learning bias here. Okay, so let's quickly go through the literature survey. So using neural network to solve PDEs are not new. So this is back in 1994. These two guys, they first proposed they first used the neural network to solve simple ODE, and then Lagares in late 90s and early 2000. He also uses neural network to solve PDEs. In recent year, ORD actually uses multi-scale model for the solution of what is called as it's basically heterogeneous media problem. Then in 2016, Brunton and others proposed Cindy model to learn the it's basically a dictionary learning for the dynamical system. So you are actually having the data and you are learning the physics behind that data. Okay, so it's like that you supply different derivative terms along with the coefficients, and you are learning those coefficients. So if the coefficient is 0, that means that derivative does not exist in the equation. If the coefficient is not 0, then that derivative is a part of that equation. So that's how the Cindy model works. And then Karpatne proposed physics guided neural network. So this is the year when PINN also came. The original paper was put on archive 2017, and Wang also proposed in 2018 the physics informed machine learning model for turbulence modeling. And the PINN paper, physics informed neural network paper, was published in JCP in 2019. So there are so many works. So in this short course, we are actually focusing on PINN more. So what is PINN? So it basically essentially defines a paradigm for bridging physical model and the observational data. So you can see that this is a typical feed-forward neural network. You have input data, x and t. X is space dimension, t is time, and u is the output. So these are the hidden layer with activation function phi. Just two hidden layer for schematic representation. And now what you are doing, you are not, so for example, you have the data available in the form of initial or boundary condition. So this is the data mismatch term. Okay, so this is the measurement loss. You can see the first term here. This is the u target minus u output, which is given by the neural network. Okay, so this is the data mismatch term. It is called as measurement loss. But now you also have one more term. So what we are doing here, so we are actually differentiating u to get all these derivatives. Again, I use automatic differentiation here. And then you actually create the residue of the PD. In this case, this is a viscous Burgers equation. And that residue is defined by a calligraphic F. Okay. And our aim is to minimize that residue. So this is the term which actually incorporates physics into the model. Okay. So now your loss function consists of not only data mismatch term, but also the PD solution, the residual of the PD. Okay. Yeah. Yes. Yes. Yeah. So you have to actually do the computational graph twice. Okay. In the first set, you get the first derivative, and then you have to feed that to get the second derivative, the first derivative value. Yes.
Then we can go for like
multiple derivative. Yes. 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 So end of neural network, we are getting mapping from input to output. Now what we are doing, we are constraining our solution to satisfy the boundary and the physics together. So what I'm saying is, this is the loss function, which consists of data mismatch term, where I am forcing my solution u theta tilde. Theta tilde is the set of all parameters. Okay. So this ground truth is the data which is coming from boundary and initial condition. Okay, so I'm forcing my solution to satisfy boundary and initial condition. And if you have data inside the domain, experimental data, you can also force that. Okay. No, you also need, so this is the PD residual, right? So in order to satisfy PD residual, you need these collocation points or residual points within the domain. No, so if you do not know the exact, because this is a PD residual, you are minimizing the PD residual. Most of the cases, you do not know the exact value. If you know the exact value, you can actually feed directly here, right? It's just a data mismatch term. But for the forward problem, what you know is boundary and initial condition, right? That has been satisfied using the first term, data mismatch term, right? Second thing, you also want the output of the neural network to satisfy PD residue. Okay, so this way you are incorporating the physics into the loss function. It will be a data term, right? So that will come into the first term, data mismatch point.
Yeah, I mean more number of points with data. So it will be easy for the network to build.
If you have, yes. Of course, if you have more data points, it will be easy for network. But which is possible for inverse problem, right? For inverse problem, you may have a lot of data, but you do not know the physics, right? So you have parameters involved in this PD residue, which you are learning along with the weights and biases. So that's an inverse problem. So basically, if you see, if you don't have neural network, then what you are doing is you are differentiating. Here I'm using automatic differentiation, right? So it also uses some kind of numerical method. I have shown the chain rule of differentiation, right, to calculate this. So this is basically some kind of numerical method. Absolutely.
Yeah, the first question that I think will come to
well, as I always say in my talk, basically PINN is good for inverse problem. Or you can also do, for example, it can overcome the curse of dimensionality. If you want to solve high dimensional PDs, then you can solve it. In our recent paper, we have solved 100,000 dimensional problem using PINN, which is not possible in traditional numerical. Or maybe I do not say if it is possible. Yes. So if you are comparing PINN with other numerical method for forward problem, of course it is not efficient. Okay, but for inverse, yes, it is.
Because in the backpropagation, it is calculating multiple differential results, partial differential. That's why it seems like it is good for multi-dimensional.
No, that's well,
being good efficient and in multi-dimensional.
For high dimensional, you are saying. No, the idea was different. We use stochastic dimension gradient descent algorithm. So that's I'm not covering here. Yeah, that idea is.
Because that's what we are getting derivative of each term.
Okay. No, we use stochastic dimension. We randomly choose dimension. Okay. We have also shown the case where you have a high dimensional PD, but the solution lies in a low dimensional space. So if we use randomly, if we choose the dimension, then we may miss the solution, right? Because it has a low dimension. But our approach seems to be working fine with that case too. Yeah. But in this case, your question is related to automatic differentiation, or
how it is being faster than numerical differentiation in multi-dimensional.
Well, automatic differentiation, as I said, first of all, it gives the machine precision accuracy, which is not possible in numerical scheme. Second thing is, I'm not, basically, I cannot say about if it is efficient than numerical scheme or not, because it all depends on your chain rule of differentiation, how many terms are there, okay? But numerical scheme, you have fixed tensor, right? So it may not be efficient, but it is accurate than numerical solution. But of course, I also said that for hyperbolic conservation law, your derivatives, AD derivatives may not be correct, because they do not care about the information from where, direction from where the information is propagated. Okay, so what we are doing here, we are solving PD. So we are recasting the original PD problem into an equivalent optimization problem, right? And with the given loss, the aim is to minimize this loss function to get the optimal set of parameters, theta star. Okay. As I already said, it can solve both forward and ill-posed inverse problem. That's one of the advantage. Let's start with the simple example. So we have a Burgess equation here, viscous Burgess equation. So you have unsteady term, non-linear convection, and the viscous diffusion term. So initial condition is just a sine pi x minus sine pi x. My boundary conditions are 0. So here I use just random 150 points on boundary and the initial. So you can see it here. So these, sorry, not 150, 100 points. So you can see this cross here. So these are randomly chosen points along the boundary, and these are the initial values. Okay. My residual points, where I'm calculating the PD residue, they actually scattered within the domain and on the boundary. So I'm using 8,000 residual points. My activation function is tan h. Learning rate, NL, you have to define, which is 8 in e raised to power minus 4. And I'm using Adam followed by the LBFGS. Okay. So you can see the results here. So I just use first 5,000 iterations and 100 iteration for Adam, and then I switch to LBFGS. So you cannot see Adam curve here. It's small blue curve. Okay. And at the end of the iteration, I got this solution. So you can see these white lines, which I'm cutting along the x-axis, along the t-axis, and I'm comparing the solution, the exact solution, blue line, and the dash red line solution here. The accuracy here, the L2 accuracy after 5,000 iteration is just order of -2, because I just ran it till 5,000 iteration. If I increase the number of iteration, you get more and more accurate results. But here I must admit that you cannot expect the accuracy like the spectral method, -12, -15. Okay, because the I'm trying to solve this equation. So what I did, I have the boundary set of boundary points and initial points, okay, given by initial and boundary condition, and I just use this as the data mismatch term using initial and boundary, and I use this PD, the viscous Burgess equation here, the residue of the viscous Burgess terms. So I got the loss function. Now here I use Adam optimizer followed by the LBFGS optimizer to minimize the loss function. Okay. Yes, I'm solving for you. That satisfies both data mismatch term given by initial and boundary condition. Okay, look at these points here, 100 points, cross points, and the PD. So I'm also incorporating PD term as a penalty term in the loss function. So neural network doesn't care whether it's a space or time direction. It just computes the derivative, the automatic differentiation. So as long as you are giving points to compute those derivative, it's fine with that. So it doesn't know what is time and what is space. For them, it's just computing derivatives. So it's like a regression. You have a data and you are fitting the problem. So this is not an evolution. You are not evolving in time. You are fitting a data. It's a regression problem. You are fitting the data as well as the physics.
So if you think incorporate the physics part of it, right? How bad is the...
So physics part, if we just incorporate, so oh, you don't. Oh, okay. Then well, if you have data, in this case we have data only on the boundary and initial, so it will not give any solution. Maybe it will give solution in a part close to the data points, but not inside. Okay, because you don't know what's going on inside. Huh? Sorry. Because if you see the initial solution is smooth sine wave, right? But because of viscous Berger equation with small viscosity coefficient, it is developing a high gradient region. If you remove the physics and if you just put the data points, it does not tell you whether it will form a shock or what, right? So this is given by the physics. It is coming from the physics. So you may not get accurate solution
away from the data points. You may get solution, close to the data points because it is available, right? The data points. Okay, second thing, if you remove the data points and just enforce the physics, again, it will give a garbage because of there are multiple solutions. It's ill-posed problem, right? You don't have initial boundary condition and you're trying to solve a PDE. So it will give a family of solutions. So it's a garbage again, right? Okay, so okay. I think, yeah. So the first question is the differentiation easy to achieve for complex PDE? Yes. You can easily achieve for any kind of PDE term. So if you see in this case, you can see the nonlinear term, nonlinear PDE, nonlinear convection term. Even you can go for higher order PDEs. But yes, we have seen that for very high order PDEs, you may get some error. I mean, it may not be machine precision accurate. Okay. I think second question is, I don't know. Yes, so 8,000 is the points which are scattered in this space-time geometry randomly. Okay. So these residual points where you calculate the PD residue. Data points where you know the solution value and where you use. So, okay, I'll just, okay. So here NU is the data points, number of data points, and NF is the number of residue points. Okay, so let's see the some of the scientific applications. So the sorry. So when you calculate the derivatives of the solution, the output of the neural network, right? You get derivative values, right? So you get derivative values, right? So you can use those derivative values to create a residue, PD residue. So in this case, I'll write it down. Yes, say for the Burgers equation. So if you have your residue f of theta is defined as mu t plus mu ux minus mu times ux. So this is the term. So I am forcing this term into the loss function. So the output we get from the neural network where we calculate the derivatives and yes, exactly. So you use automatic differentiation to get the derivative, and you create this residue, and you just feed it to the loss function. No, this is, so what you have is just a L2A on that. So what you are doing, you are actually minimizing this loss function, right? So you are minimizing means you are actually going towards solution which admits this PD. Yes. No, it is defined. Only thing is this is a parameter. So you need to initialize this parameter with some values, say 0.1, and then update this mu along with weights and bias. So what neural network is doing, it is also updating this mu value so that the data, it will satisfy the solution output, the output of the neural network, which is the solution of PD, satisfies data as well as this. Okay, so first application is the high-speed flows. So here, the aim is to solve the inverse problem using Schlieren data. So this is basically an experimental technique where you can actually get the gradients of the density for the flow. Here we also use some pressure data and inlet condition. So if you see this XT, this domain, this is basically an XT plane. So the left-hand side is the inflow direction, right-hand side is the outflow direction, the bottom is the wall, and top is again the inflow direction. Okay, the flow is actually coming from left to right. Okay, and since it's a high-speed flow, it's Mach supersonic flow basically above Mach 1. So you get a oblique shock wave here. Okay. So we use two different types of training data. So we use this randomly distributed PD residual points. And here we use the points which are actually coalescing along the shock wave. Okay. Okay. The point here is we can choose the residual points because it's an inverse problem, right? So I have the data from Schlieren, where I can see where is the high gradient of the density and where is there is no gradient. Okay, so I can coalesce more data points along the high gradient region. Okay. Okay, so aim is to identify the gas constant gamma here, which has true value 1.4 air. Okay, so if we just use clean data, exact data, the random points, distributed points will actually converge to 1.46, but actual value is 1.4. But the cluster points will give you 1.39, close to 1.4. The reason here is the gamma is very sensitive to the orientation of the oblique shock wave. If you slightly change the orientation, you will get different value. Yeah. Okay. Okay.
So the thing is, let's say I want to implement this. So all that we do is you have the loss function, the loss function coming from Ameya.
Yes.
And then you just put the additional thing as like an epsilon.
Penalty method.
Yeah, this is the penalty.
Yes.
And then just run the algorithm.
Yes. Yes. That's it.
There is a price that it's actually giving you interior,
Solution.
yeah, the solution will be here.
Yes.
Better, just to incorporate in this.
Yes. Yes. Because it is also satisfying the PD. Yes. So at every point we are calculating derivative using automatic differentiation, creating this loss, and then trying to satisfy that at each and every point.
You get the solution for all space variables.
Yes. 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 The whole. So it's like a fitting problem. It's a regression problem. We are not evolving like a numerical scheme. You know, there is no time evolution concept here. So there is no question of stability. For evolutionary PDs, you need to satisfy certain CFL condition or something like that. But here, it's just fitting, regression problem. Yeah. The boundary conditions. So, well, in this case, it's a zero value. So what's your question? Well, no slip condition, yes, the velocity will be zero on the wall. Yeah, yes. What do you mean by which point you are talking about? The initial value? Yeah, it is non-zero, but the boundaries are zero, right? It's just a value. You are giving it to you're feeding it to the neural network, and you're asking it to satisfy through this first term. So neural network doesn't, I mean, it doesn't care whether it's zero data or non-zero data. It just tries to match. So for example, if I'm solving a fluid flow, which you mentioned, where with no slip boundary, or sorry, yeah, no slip, and you have U and V and W velocity, 3D, where velocity is 0 on the wall, right? So I'll be having three terms, data mismatch term for each velocity component, right? And I'll force my velocity to be equal to the target value, which is 0, along the wall. So all these NU value will be on the wall, NU points. So neural network, they just need a value. That's it. So it doesn't matter whether it's 0 or non-zero. Okay. How do you decide where is the discontinuity and the criteria of refinement? Well, we are not defining, we are not deciding the discontinuity. As I said, we are just. Oh, okay. I thought he is asking from the Burgess equation. Oh, I'll come to that. How to minimize this? Oh, okay. Oops. Okay. Yeah. Thank you. Okay. So the question is how you are deciding the I guess the location of discontinuity. So this is, as I said, this is an inverse problem. And we have that data available from Schlieren technology, okay? That gives the gradient of the density. And since this is an oblique shock wave, the density is constant away from the shock wave, but across the shock, the density gradient jumps, okay? So now we know the location where density gradient has large values, and then we can coalesce the point along this high gradient. These are just the points. These are residual points I'm showing. Okay. If I choose randomly, I'll get one solution which is not accurate. But if I coalesce along the high gradient region, which is available from Schlieren, then I get more accurate data. So this is for the clean data. But if I increase the noise, so for example, whatever data I have, I'll just increase I'll just add 1% noise or 2% noise. Then you can see that the solution of both random and cluster data point actually degrades, because that is expected because of the noisy data which is available. So in this case, with 1% noise, it's 1.31 with random data points, training points or residual points. This is again 1.40, but still with cluster data, your solution is more or less accurate. Okay. So second is the quantification of the material. So here, what we have done, we have actually infer the properties of the material. This is a polycrystalline nickel alloy. And here aim is to infer the spatial variation of compliance coefficient of materials using only displacement data. Okay, that is obtained from experiment. So actually, we obtained X2 displacement from this experimental technology, laser vibrometry detection. This is given by the US Army. And we also have X1 and X3 displacement data that we actually obtained from the FEM solution. Okay, so exact data for displacement in X2 direction and high resolution synthetic data for displacement in X1 and X3 direction. I'm not sure if it is even visible. Can you see X1, X2, X3 or not? So it's basically you have the stress strain coefficient, the Hooken's law. So where you are actually having, if you have stress, you can find out strain and vice versa, right? So here, what we have only the displacement, and we are trying to find out what kind of material is. So compliance from compliance coefficient, you can find out the material properties. Okay. So I'll come to that. I'll show you how we are finding. Yes. No, nothing. So this is again an inverse problem. Okay, so you cannot solve this kind of problem using any numerical method, right? Okay. So basically what we have is the polycrystalline nickel material. And this we again use pens. And this is actually, again, we do not know physics here, but yes, we know the Hooken's law. No, and the elements of the compliance coefficients are the parameters that we need to identify. Okay. After training the model, you can see we are just matching the actual data with the simulated data, and PIN is actually matching well. So this is just a wave which is propagating in the nickel alloy. It's a slab basically, and the wave is propagating. Okay. So for a single crystal nickel alloy, the speed of second shear wave mode is around 2.97 millimeter per microsecond. Okay. So, and these are the compliance coefficients. So you can see the left side is the speed of space dependent second shear wave mode. And you can see the variation. It is from 2.95 to 3. Okay. So it actually shows that it is a nickel material, but it is a polycrystalline, because you can see it varies from 0.25, 2.9 to 3. So although we are not, we couldn't capture the boundaries of the crystals, but we can still say that this is a polycrystalline nickel material. Okay, that's from the speed of second shear wave. Okay, yeah. No. What I'm saying is, I'm showing you this color bar. The color bar is from 2.95 to 3. That is a coefficient, right? Okay, that's the second speed of second shear wave. Okay, this is actually a speed of second shear wave for single crystal nickel, which is 2.97. So this confirms that this is a nickel alloy, right? No, this plot is speed in the whole domain. Yeah. Every point in the whole domain. Yes. Well, I'm not showing all the coefficient of the compliance matrix, but I'm just showing one coefficient. Second shear. Okay. Moreover, it varies from 2.95 to 3. So it actually confirms the presence of polycrystalline material, not a single crystal. So we couldn't capture the boundaries of the crystal because we don't have enough data, but it confirms that it is a polycrystalline nickel material. No, it's so the material can be consist of a single crystal or polycrystal, right? So we are just confirming it's a polycrystal. It's not a single crystal. Output of, yes. And here, this is just a spatial variation of C44. That's the compliant coefficient. Yeah. Yes, we have also done that study. So, not in this case, but if you reduce the data set, obviously your solution will decrease. The accuracy of your solution will decrease, right? The predictive accuracy. You're talking about inverse problem or forward problem? Because data set is common for both. So if it is an inverse problem, definitely if you reduce the data set, it will decrease your accuracy, right? And if you increase it, it will increase. So it all depends on problem at hand. I mean, if you're asking how it is, the rate at which it is decreasing, it all depends on problem at hand. Okay, let's move on to the another example. So it's an inverse water wave problem. So basically, our aim is to infer the velocity field, okay, from the and the corresponding forces on the walls. If you have any object, and you want to find out what are the forces which are acting on that object because of movement of this fluid flow. So here we use only water column height, okay, as the given data. Okay, so you can see Okay. So this is eta is the eta is the water column height and the first row, and u is the transient velocity, which is the second row. Okay, so you can see these black dots here. So these are the so again it's an xt plane. Okay, and what we are doing, these are 12 lines. Okay, so these are the locations along the x-axis where we are placing a sensor or gauges, which gives you the value of eta in time. So how the eta goes, at that location, was the value of eta in time. So you have a wave which is actually going, okay, and you are just measuring the water column height at fixed location. So that's why you will get these horizontal lines, because your vertical axis is the x-axis. So you have 12 gauges here, which we placed, and we are actually finding the eta value as a function of time. In this case, we have 20 gauges. Okay, so this is the only data which is available from the experiment, and along with the data, we are also enforcing the physics. Okay, so if you can see the predicted value of eta here. So we don't have data in this zone. You can see this. We have data till x equal to -35. Okay, we don't have any gauges in this zone because nothing is going on actually. So you can also see the point-wise error in this for 12 gauges and 20 gauges. Moreover, we have this water column height, but we don't have anything on the velocity, but still it can actually captures the velocity really well. So you can see the point-wise error for both cases, 12 gauges and 20 gauges. So obviously, if you increase the number of gauges or the data points, your error will actually become lesser and lesser. So you can see that the maximum point-wise error is 0.06 here, and here it's 0.02. Okay, so that was the answer to your question. I mean, how well it decreases. Let's see another example. So you can see the wave. This is a symmetric problem. So we just take the upper half portion. Okay, so this is the wave which is coming, and it is hitting this rod here. So this is a square rectangular rod. Okay, since it's due to symmetry, we are just taking upper half, but the wave is also there on the right side. So you can see the schematic representation. So this is a rectangular block, okay, small block. And in this case, we are actually taking a mixed value. So we have a low fidelity gauges, which gives you a low fidelity data points, data values, and we have high fidelity gauges, which gives you it gives you high resolution data, but they are very expensive. So the number of high fidelity gauges are around 50, but the low fidelity gauges are around 1,000. Okay, yeah. Because well, there are many techniques to deal with noisy data. So people have also proposed Bayesian pins. So they take care of the noisy data, and basically your output is not a point estimation, but a distribution with a confidence level. Okay, but here we are not doing that one. So we have low fidelity data and high fidelity data. So what we are doing, we are trying to learn the correlation between these two, and then map the low fidelity data into high fidelity. So we will see that in upcoming lecture slides. So here is the predicted low fidelity water column height and the reference water column height. So we basically use multi-fidelity PINN network. Okay. And these are the force values. So we have 3 walls, wall 1, top wall 2, and the right side wall 3. And these are the force values on these walls. These are all normalized value. Okay, so the reference is given by black and the solution is given by the red curve, red dash curve. So you can see that it matches really well, and these are the point-wise error below. So the minimum error is of the order of -4. Okay. This is a pretty smooth solution. So error is, you will get a pretty much accurate result. So again, as I said, this is an inverse problem. The only data you have is the water column height. You don't have data on velocity. Well, you can actually put velocity data if you have wall. So it's just reflecting boundary condition, but you don't have anything inside the domain. Okay, so there are, yeah. Yes, velocity, which I have shown here, and the forces. Forces on the wall. Yeah, what are the forces which are acting on the wall? Okay, so there are vast literature on pins. It has already been cited by more than 6,000 papers, and we'll discuss some of them. It is not possible to discuss all. So in this talk, in this short course, we'll discuss domain decomposition based PIN, which is conservative PIN and extended PIN. We'll also discuss variational pins, where they use this the variational framework. And then, as I said, the multi-fidelity pins. And then there are so many things like fractional, non-local, stochastic pins for higher dimensional Bayesian ensemble parareal pins. Homo pins is for finding the multiple solution, and so on. Okay. Okay, so let's start with the first one, domain decomposition base. So the classical approaches to tackle the high data or large data or model problem is to, first one is data parallel approach. So you have data, big data, which you can split into number of chunks, which is equal to number of processor. And then model, neural network model is initialized with the same parameter for all the processors. So you can see here, you can split the data. We have 4 GPUs, so you can split the data into 4 and then feed that data to the same neural network model. Okay. Then you get the loss function for each, from each GPU. Okay. Okay, so that's the different loss function. You get J1 to J4, and then distributed optimizer is used, which average out the loss gradients with all this all reduce operation, and then this average gradient of the loss you send it to the processor in the communicator world through the broadcast. Okay, and then you update the values of weights and bias. Since you have a single network, fixed network, your weights and biases will be the same, which you will update in the next iteration. Another approach is model parallel approach. So you just split the data into batches, in this case B1 to B4, and then feed this data. And if you have 4 layers, you can actually give each layer of the neural network, these are hidden layers, to GPUs. Okay, and then each layer will process this data sequentially, so in a pipeline approach. So once L1 started finish working on B1, it will send B1 to L2, and then it will start working on B2. So that's the forward pass. And once all the data is processed, the backward pass kicks off, and then again finishes the operation in a pipeline mode, starting with B1 till B4. Okay, and at the end you update the weights and biases for the model. Third approach is a tensor parallel approach. You have the weight matrix, you split the weight matrix column wise, and use different GPUs for different columns, and that's how you can actually make it parallel. Okay, so if you see all these approaches, data parallel, model parallel, and the tensor parallel approaches, they use a single neural network. So our approach is the domain decomposition based pins. So basically you have domain, you can split that domain into a subdomains. Okay, and you deploy pin in each subdomain. Okay, instead of single pin over the whole domain, you use different pins in each subdomain. Okay, now you have already seen this figure before. Okay, so you have a neural network. The output of the neural network matches the data as well as the physics. But now you have one more condition here, which is the interface condition. Okay, because you need to stitch these subdomains together, right? So how you will stitch? Using some kind of interface condition, maybe continuity of the solution or whatever, right? Yeah. It's not mesh, but it's randomly. You can choose. You can decompose that in any fashion. Yeah, it's not mesh. It is still the mesh-free framework. The residual points where you are calculating the derivatives, they are all random points. Yeah. So for example, if you are solving a very big problem, 3D space-time, 4D space-time, right? And you cannot, if you want to solve it parallelly. So this is the parallel approach for it. You just domain decomposition this. No, but then you can impose flux continuity condition. So we have done that thing in our paper. Of course, we cannot enforce the continuity, but we can enforce the average continuity condition. I'll come to that. Okay, so now again our loss function, data mismatch term, PDE loss, and then we have additional interface loss. Okay. Okay, so what's the advantage? Parallelization capacity, right? Which was already there with the other model, data parallel, model parallel, and the tensor parallel approach, right? But now we have additional 3 advantages, which I have shown in blue curve. So it has a local representation capacity. That means I can choose the neural network. Say, for example, in this case, I can choose a deep neural network. For other, I can choose shallow network, right? So the representation capacity of the neural network increases with the architecture. I mean, what are how deep it is and how what are the how many number of neurons you use. Okay, so that's the advantage. Second one is efficient hyperparameter adjustment. So I can choose learning rate, activation function, all the hyperparameters separately for all PIN. I don't have to stick to one case. Okay, so as sir mentioned, if you have shock wave, so it may be lying in this, so it is just cutting in this zone, so it will be lying in this 3 subdomain. So this is a complex feature, right? So I need a deep neural network, but rest of the subdomains, the solution is constant. I don't need a deep neural network. I'll go with this shallow network, right? So this way I can adjust all the hyperparameters and the representation capacity. Since we are enforcing the interface condition, we have also seen that it reduces the error which propagates in the domain. So basically how the error propagates, you have the data points on the boundary if you are solving a forward problem, right? And when neural network it learns from the boundary and it goes inside the domain. Okay, so the error increases more if you have, say, for example, you are doing a long time integration. Okay, so you will see that the error towards the initial condition will be less, but as you go for a long time, the error will be more here. Okay, because you don't have much data, you have just boundary condition. But near initial, you have boundary and initial condition, right? So when you enforce the interface condition inside the domain, we have seen that it reduces the propagation of error in the domain because you have additional solution value constraint, basically. Okay, so let's start with the first domain decomposition based method. It's a conservative pins. This is basically tailored for the conservation loss. So what we are doing here, these are the interface conditions for the qth domain. So basically there are q domain subdomains. So the first condition is the flux continuity condition. That's what I just mentioned. And the second condition is the average continuity condition. So if you have smooth solution, you are enforcing this point. But if you have discontinuous solution, then you're actually enforcing the average solution, average point. Okay. So this is the average term between the neighboring networks. This is the average solution. Okay, let's come back to the same Viscous-Burgess case. So now I have decomposed the domain into 4 subdomains. You can see that these white lines. So subdomain 1, 2, 3, and 4. Okay, and Okay, so this is the error here. You can see the error, and these are the relative L2 error. You can see with average term, which is the blue. Sorry, without average term, which is the blue curve, and with average term, which is the red one. So with average term, it actually decreases faster. I just enforce the flux continuity condition, no average continuity. But in red, both flux and average. Extra, yes, penalty term, yes. These are the examples of lid-driven cavity. It's 2D incompressible flow. I just decompose the domain into 12 parts. And these are the number of layers, number of neuron, and number of residue in each subdomain. And this is the comparison. I just compared that with GIA. GIA is the experiment. I mean, these are the numerical values which is available online. And I compare the recipient results with GIA, which matches perfectly. This is again an inverse problem, Burgess equation. So this is similar to what I just explained. So you have a data, given data for Burgess, viscous Burgess equation. And what so I do not know the equation. So what I'm doing, I'm actually sending a library of terms. So you have unsteady term, non-linear convection. You have again a linear convection term. You have viscous term, and you have a dispersive term. And these are all having coefficient alpha, nu, and beta, nu, and alpha. Okay. So the aim is to identify these coefficients. So now, if your given data is a viscous Burgess, we know that only nu will be non-zero, alpha and beta should be zero, right? So once we start training, so it's the same model, domain decomposition. We have 4 subdomains. I initialize alpha, beta, and nu value, 4 different values in 4 subdomain. Okay, and now you can see that once the training start, it actually comes together, all the values, and then alpha goes to 0. Similarly, data is given by viscous Burgess equation. So it is the same data in XT plane, randomly chosen points. Yeah. So interior, yes. They are not for inverse problem. When you say inverse problem, you should have some data inside the domain. If you have just boundary data, it may not be enough to get the solution. Yeah. So in this case, when you are enforcing the physics in this form, but we have not done that. But yeah, in the literature, people have done. So they have only data on the boundary. So basically, it's a forward problem, but still some physics is missing in the model in this case, right? So they were still able to get the solution inside the domain. Okay? But in this case, what data we are using, it's within the domain, not only on the boundary. No, so what we are doing, it's a continuity condition, right? So on the interface, we are forcing them to be same. So that's why they are converging, and then together they are going to 0, right? And you can see that till they have not attained 0 value, the new value is going arbitrarily. It crosses the exact value here, but it was increasing. The moment they converge to 0 value, it started coming to its original, towards its original exact value. Okay. So this I had done it for 160. I think it's 1.6 lakh iterations. Yeah. So you still need some more iteration to exactly get that value. But it all depends on the data. As sir mentioned, if you reduce the data, or if you just take boundary data, you need a lot of time to converge, because you don't have enough information, because again, your model is uncertain, plus you don't have enough data. So it will take a lot of time to converge. Okay, so here is the comparison for exact and CPIN. So it will not give exact 0, but till -6. And this is mu value, 0.0031 and 34. One important thing here, you have to normalize the data, the equations. So for example, if you are solving a Maxwell equation, you have speed of light 10⁸ 8, right? So you cannot put the dimensional form of the equation into PINN. It will not converge to such an high value, okay? Because it all depends on your learning rate, right? If you want to infer your speed of light 10⁸ and you initialize at just 10, you can imagine how much time you need just learning rate of -4 to go from 10 to 10⁸. So you need to normalize, non-dimensionalize your PDs before feeding it to the neural network.
Data is given by distant subject, but the physics informed part is pure that long equation.
Yes, yes, yes. And we are trying to infer those parameters in red, beta, nu, and alpha.
But because the data is given what is it, beta and alpha should be zero.
Yes, yes. Okay, so we can actually use this domain decomposition strategy not for only conservation laws, but any PDs, right? Or maybe it would be beneficial if we can use it for space-time domain. Okay, so the answer is X-PINN. Yes, you can use it. In this case, again, we have flux average solution continuity condition. We don't have flux continuity. This is not a conservation law. And second is we have the residual continuity condition. So what we are doing, we are forcing the residue of the PD to be continuous. Basically, it's a 0, right, along the interface point. And if you have any other additional condition like the integral constraints or some derivative conditions, continuity condition, you can also enforce. So advantage over CPIN, you can extend it to any differential equation, right? You can actually do generalized space-time domain decomposition, right? You can also decompose in time. That's the advantage. And interface conditions are simple because in CPIN, you have to enforce the normal flux continuity condition. So you need the normal direction if the interface is complicated, right? Here, there is no normal direction. It's just residual continuity conditions. Okay, so implementation is simple. This is the comparison for PIN, CPIN, and XPIN. So spatial domain, you can do it in CPIN and XPIN, but not in PIN. Parallelization capacity is there in CPIN, XPIN. Local representation capacity, efficient hyperparameter adjustment. And as I said, you can apply XPIN for any differential equation and not necessarily conservation laws. Interface conditions are simple in XPIN, complex in CPIN. And yes, XPIN has spatio-temporal decomposition. You cannot do it in CPIN. It's just for spatial decomposition. Again, Burgess equation. Now my domain is not a rectangle, but you have a dolphin-shaped domain and the outer blue C domain, which is domain 2. These are the hyperparameters which are used. And this is the solution. So you can see that the predicted solution is really well. The error is -3. I just ran it for first 20,000 iteration here. But you can see it can also handle a complicated subdomains easily. I'll quickly go through this. So this is again a 2D compressible Euler equation. Okay, so you have a shock wave. Okay, and I have a peanut-shaped domain. So the shock wave is actually penetrating the peanut-shaped domain, inner domain, hitting the lower wall and then reflecting it back. So you can see the solution here. So again, I use continuity, the flux continuity. This is a combination of CPIN and XPIN. So I use flux continuity condition along the interface and solution continuity, average solution continuity condition. So this is the comparison with the exact solution. You can see it captures the shock well. Okay, I'll skip the parallel implementation. This is just to show that I'll show you the main results. So this is the weak scaling for XPIN and CPIN. And we have also done strong scaling. So we can see the speed up for CPIN. One thing is important here is CPIN just matches the flux continuity condition, which has low order of derivative compared to the the whole residual continuity condition. So that's that's why C-pin speedup is more compared to X-pin, and they almost hit 80% efficiency for C-pin and 70% for X-pin. So I think I'll start variational pin in the second class. Before that, we will in the second class we will solve the we'll see some coding examples. Okay. I'm supposed to finish this lecture 1 in 2 hours, but I couldn't finish. So yeah, we'll start with variational pins. Okay. Yes, it is without refinement. So basically we have already okay, so yes, we have already taken large number of points, so we don't have to do refinement here. So, and plus we also have the boundary condition. Here we have the inflow boundary condition on top and the left wall. Bottom is the wall, and right one is we have extrapolation boundary condition. So we don't have to do refinement. Should I stop here?